We are now ready to look at our final chapter, the final chapter being the chapter concerned with entropy. And so I'm going to go ahead and share my screen here. Oops, okay, I need to. Okay, so in chapter 6, based on what was discussed in chapter 5, the concept of entropy is defined. And most importantly then, what we are looking for is the change of entropy as we go from one equilibrium state to another equilibrium state due to some type of change. So in this particular chapter, we recognize that once we have defined entropy, one of the equilibrium or one of the property diagrams that tells us a lot is the temperature entropy diagram. And so we'll be discussing that. One of the reasons why that's so useful is because changes of entropy imply irreversibility sometimes. And we're always interested in seeing what if there is any entropy change in a process. And on a TS diagram, that would show up as a vertical line where temperature is plotted against entropy. One of the things that I always bring up is that there is no such thing in thermodynamics as the conservation of entropy. Okay, entropy is the equations that we have for entropy are only a balance of entropy as opposed to a conservation of entropy. Entropy can be destroyed, okay, and we will see that entropy can be produced. And so we will be looking at that as we go through our various processes. And so one of the first equations that with the definition of entropy is the entropy balance associated with a closed system. If a closed system is going between state 1 and state 2, and during that closed system there is some heat transfer that occurs across the boundary at a given temperature, the change of entropy associated with the system, the closed system entropy change is given by this expression right here. What we see is we see the integral form from 1 to 2 of the heat transfer across the boundary at a given temperature, but we also have this plus sigma term, and this sigma is always a positive. Sigma corresponds to entropy generation or irreversibility. And so in this particular equation, if this is always a positive number, we see that the change of entropy is given by this plus some additional. If there was no entropy production, this term would go to 0, and our change in entropy would just be this term right here. And so if there is no change of entropy, we have what is referred to as a reversible process. And so a reversible process is defined as the area under the TS diagram. Now, if you look at this equation, what one sees is if one actually plotted the process from 1 to 2 on a temperature entropy diagram, what one would see is that the area under that curve would be equal to the heat transfer. And so we can draw an analogy to the area under the TS diagram, very similar to what we did when we had a pressure volume diagram for a closed system. A pressure volume diagram, the area under the PV diagram corresponded to work that was done on or by the system. We can say a similar thing for the heat transfer in a closed system and how the area under the TS diagram is related to the heat transfer. The equation can also be written in a time rate fashion. The rate change of entropy is simply related to the heat transfer rate and the rate of entropy production sigma dot. When we are dealing with an open system, the control volume, we can also have a balance equation for the control volume. We see the rate equation here, the rate of entropy building up or decreasing inside the control volume is due to heat transfers, but there's also entropy flowing in and entropy flowing out. And so because it's a control volume, we have to account for the fluid passing in and going out, bringing with it entropy, some of which may accumulate, some of it may deplete. And so we have these three terms, but we also have a production term. And so the rate of entropy being generated or accumulated in the control volume is equal to this. If it's a reversible process, if there is irreversibility, there is an additional production of entropy during that process. If we have a steady system, the left-hand side just goes to 0, and we then have the right-hand side being equal to 0. But again, keep in mind that it's just a balance equation. It's not a conservation equation. Entropy can be destroyed and produced. With that in mind, we can define for various devices something called the isentropic efficiency. Since a device, if a device causes the fluid to pass through and work is extracted, such as what happens in a turbine, if we can do that in an isentropic fashion, we would get the most work out of the system. In reality, though, we don't get as much. We don't extract as much work out if we have irreversibilities. And so this isentropic turbine efficiency is simply defined as the maximum amount of work that can be obtained as we allow a high pressure fluid, high temperature fluid that expands to a lower temperature, lower pressure fluid. The denominator here would be the maximum work that we can obtain out of that system, and we divide that into the actual work. And so the actual work would be going from state 1 to state 2, and that will be a lower number. If it's a nozzle that we're dealing with, the purpose of a nozzle is to generate or is to facilitate the fluid in terms of velocity, to try to increase the velocity or the kinetic energy. And so a nozzle, whose purpose is to create kinetic energy, if that creation process is done in a isentropic fashion, the maximum kinetic energy would be obtained. But in reality, because of irreversibilities such as friction and other things, we would actually not generate as much kinetic energy. So the nozzle would have an efficiency. If we have a compressor or a pump, we have then devices that require work to cause the enthalpy to rise. And so if we were doing that in an isentropic fashion, the minimum amount of work that would be required is now put into the numerator, because it will actually take more work than what we would expect if it was done isentropically. So the difference between a turbine and a compressor or a pump is that the efficiency is the isentropic over the actual as opposed to the actual over the isentropic. Now, when we're dealing with ideal gases, once again, if we're interested in the change in entropy, unlike the case when we had internal energy and enthalpy, only a function of temperature, now we have entropy that is a function of both temperature and pressure, or temperature and volume. So we actually need two thermodynamic states in order to define the value of entropy anywhere. And so now when we talk about the change in the entropy, we see that we can define entropy by two thermodynamic states, temperature and volume. And in doing that, we then have this form of the equation. In that form of the equation, you see that there's a temperature term, and then there's also a volume term. In this, if we assume C sub v is constant, then the C sub v comes out of the integral, and we now have C sub v, and we have the log of the temperature ratio, just like we had the log of the volume ratio here. So when we assume constant specific heat, we have a simplified form here. So this is the change in entropy if we are defining entropy with respect to temperature and volume. If we define entropy in terms of temperature and pressure, we have a similar form of the equation. We have the integral here, the temperature term, that involves the C sub p and not the C sub v. We then also have a term involving the change in pressure. And as you can see here, again, as C sub p is constant, and C sub p is constant, we can eliminate it from the integral and take it as a constant in this particular point. And then this R log of pressure comes down here. So this is the equation similar to this equation here, corresponding to a constant or a pressure temperature relationship with respect to temperature, with respect to the entropy as a function of temperature and pressure. Now this term right here has been tabulated for various gases and is been provided to you in table A22, and they call that the S0 value for air. So if air, because we know the C sub p is a function of temperature for air, that can be evaluated and tabulated such that we can, for a given temperature, we can then determine that value, and that would correspond to a pressure, a reference pressure of 1 atmosphere. So that number can be obtained out of the tables, and then you have the pressure effect. Now I want to just say a couple of things here as associated with these two equations here, the change of entropy. What we see in both of this equation 621 and this equation 622 is that temperature has an effect on entropy change. As temperature goes up, as we go from T1 to T2, the log of that is a positive number. We see an increase in entropy. And we see the same thing down here. Because C sub p and C sub v are just constants, positive constants, as temperature rises, we see an increase in temperature. If temperature went down, we see a decrease in temperature. And that makes sense because we understand entropy being a figure of disorder of a system, and the higher the temperature of a system, the more disorder is associated with the system. The second term of entropy needs a little bit of discussion, and that here you see that if the volume increases as we go from state 1 to state 2, An increasing volume means that the system is going to a more open, a more random, a larger state. And so that makes sense that this term here gives rise to an increase in the entropy. If we compare what happens when the pressure increases, we know that when pressure increases, we are taking the system, we're forcing the system to be at a more confined, smaller system because of the effect of pressure. And so as we increase pressure, the effect of an increased pressure has a negative effect on the increase in entropy. So temperature can go up and pressure can go up, and those two could actually cancel each other. And so we could have a non-changing entropy process with both temperature and pressure rising. It's just that one counteracts the effect of the other. Likewise, if pressure decreases, then this log term is negative. A negative negative is a positive. That gives rise to an increase in pressure. So we could say the same thing. Temperature could go down, and pressure could go down, and you could still have these two competing effects causing no change in entropy. Now, because of this effect here, table A22 also provided for you. It looked at this equation right here and said, what happens when there is no change in entropy between a temperature and a pressure condition? And so table A22 provides these two additional table entries called the relative pressures and relative velocities. And they can only be used if you assume that the substance at hand, which in this case was air, is undergoing an isentropic process. If it's undergoing an isentropic process, and if you know the pressure ratio, then this ratio is the same, and you could then, if you know what happens to the temperature, you can then determine the final state. And so that's kind of a special effect using this table. Because we're using software, we really won't have to worry about the use of this particular table because everything is built into the software itself. The final thing is, again, when entropy is constant, and you have what's referred to as a constant specific heat ratio, K. K is just equal to C sub P over C sub V. And for a substance like air, that value is 1.4. C sub P is always 40% greater than C sub V. Any gas has a ratio of specific heats. And if you have any gas other than air and other gases, and if you have an isentropic process, that isentropic process then allows us to determine for a given temperature change what happens to the pressure. For a given pressure change, what happens to the volume. For a given temperature change, what happens to the volume based on this ratio. So these are very important relationships. These allow for calculations of pressures and temperatures and volumes when a gas is undergoing an isentropic process. Well, with that, we'll now finish up and we will start looking at some of the systems, beginning our discussion of exergy, as well as going into all the different types of cycles. But after we finish this, we're going to look at the final exam that you had in ME 3200 last semester, and we'll start going from there. Okay, that's the end of this. I'll go ahead and shut this down.